Okay, so what we ended with last time was the statement of Faraday's law. We're going to explore Faraday's law in some detail over the next today, and then going further into the next couple lectures. But before I do that, I mentioned I want to do a little bit of a sidebar on the velocity selector and the Hall effect. This is something that is not entirely related to the thread of what we've been talking about, but I want to take some time to talk about it. So first of all, the velocity selector. This was a problem that was on your homework. The basic concept and everything you needed for the homework wasn't too challenging. I just want to talk a little bit about this system, partly because it has some application to the Hall effect. So what you have is a capacitor that you've charged up, something like this, let's say. And if you charge it up like that, it's going to create an electric field, something like that. I guess let me put this label off to the side so it's not too in the way. So you can send a charged particle into this region. This is not one of the charged particles that's trapped on the capacitor plates. It's a free charge flying around in free space. And we learned, of course, that positive charges feel a force with the electric field. So this is going to feel a force like this. And if it were left to its own devices, the chances of it actually making through this gauntlet and slipping through the plates of the capacitor are pretty small, especially if we put up some kind of barrier, so that the only place that you can really get out is directly across. So in this case, if you're originally heading for that hole, you're not going to make it because the electric field is going to curve you downwards. So the velocity selector, what it does is you don't just use the electric field, you also apply separately a magnetic field. Let's say the magnetic field points like this. Let's say it points into the page. So let's suppose it's a uniform magnetic field. At this point in time, we are even capable of saying what might cause such a thing. A solenoid, right? A very long solenoid can cause a uniform magnetic field. We point our thumb along the direction of the magnetic field, and the current must wrap around something like this. So there's probably current on the outside here running like this. So again, double check it. Current runs clockwise. Magnetic field points like that. Okay. So now the charged particle that's shot into the velocity selector has not one but two fields to contend with. We go ahead and do our slap rule. It's a positive charge. We slap B into B. So B into B. B forces up. If it were just that force, then of course this charged particle would be curved upward and eventually into a circle. But the whole point of this device is to tune it so that the two will cancel each other out. And then the particle will actually go undeflected. And it will actually come out. So it can make it through the narrow opening on the other end, because the two forces cancel. So in your homework problem, really all you had to do is set these two equal to each other. QVB sine theta. Sine of theta is 90. And Q times E. And you solve for the condition under which this can happen is when the speed of the particle is only a certain value. So E over V. Literally, if you have the capability of tuning the electric field strength, the magnetic field strength, you have the ability to select out particles. Okay? And the reason why it ends up being a velocity selector is because that's the only thing that is included in the magnetic force that is not in the electric force. So that's the thing that survives. Okay? So the charge itself canceled. The charge doesn't matter. The charge doesn't matter because both forces depend on the charge. Hence, when we want them to cancel, it's irrelevant. Just to give you an example, if you made the charge twice as big, Well, that would double the electrical force, but that would also double the magnetic force. So they're still going to cancel, right? That's why it's called a velocity selector and not a velocity and charge selector. The charge can be whatever you want. It'll still come out undeflected. You can even go so far as to switch the sign of the charge. If you switch the sign of the charge, then the electrical force will be up now, but the magnetic force will be down now. If they were going to cancel before, they'll still cancel now. So this whole device basically selects out for only velocity. It doesn't matter if the particle is charged more or less. It doesn't even matter the sign of the charge. This is the only thing that the selector is going to select out for. Convince yourself that if you're going faster than this magic speed, you'll curve and hit the top plate. And the reason why is because, of course, if you go faster, the magnetic force is stronger. The electric force doesn't care. So if you go too fast, faster than this speed, you'll curve like this. And if you go too slow, then of course the magnetic force is weaker. And you'll curve and hit the bottom plate. You won't make it out the gauntlet. Okay? So this is a velocity selector. I guess I should say a few brief words on what the heck this thing might be useful for. Well, imagine over here that you have a chamber of gas where things are ionized. So you have an ionized gas. So let's say you have a bunch of things flying around. That's very typical that when you have a gas, in fact, I should say it's mandatory for the gas to have a variety of different speeds in it. Even if you were able to get that chamber of gas to a perfectly uniform temperature, common misconception is just because it's a uniform temperature, that means all the gas particles are flying around exactly the speed. That is not true. It is more likely, the higher the temperature, for the particles to be moving around faster, but it is a statistical distribution, and even in a very high temperature gas, you're still going to find some small percentage of very slow moving particles. So this is basically a way to sort out a gas and only pick out certain particles at certain speeds and leave the rest behind. They will not be able to make it through here because they will either curve down or up depending on if their speed is higher or lower. So why might you want to do this? Well, let's suppose we have this chamber of ionized gas. We put it through a velocity selector, so we've selected out for the exact speed that they're all going to go. Okay? And then we let them enter a chamber where there is only a magnetic field. And we, of course, learned that charged particles, once they enter a magnetic field or cutting directly across the field line, they're going to curve into a circle. In this case, we've taken away the downward electrical force. The upward magnetic force is going to cause this thing to curve in a circle. We learned that the radius of the circle, and this is one of the important formulas that you need to know, which is not available, so make sure you can get it, R equals mv over qb. Now, we've controlled for the fact that they're all basically singly ionized. Let's say they're all positively charged, plus E. That doesn't mean that they're a proton. It means that there's some big, huge atom that we've taken one electron off, right? We can control for the magnetic field strength, and this is key. We've just controlled for the speed, which is the hardest thing to control for, okay? Because you're liable to have a bunch of different speeds in your distribution. We've now taken out all of the tiebreakers except for mass. So what we're going to find is that the more massive the ionized gas particle is, the larger radius turn it will make. So we can put little bins here, and we can know that if something makes a slightly smaller radius, it's going to have less mass, and if something has a slightly larger mass, it'll fall over here. So we can basically shift what is in these bins. We can sort them out and get a sense of what's there. So this thing is basically a simplified model of a mass spec, right? You guys talk about those? Okay. So you basically count how many particles fall into each bin. You're basically counting the ionized gas particles, right? You can turn any sample into a gas. And if you find, hey, I seem to be getting 2 parts hydrogen gas, particles to 1 part oxygen, hey, maybe this sample has some water in it, right? So these bins kind of set you up to have an analysis. What you guys do is you take a look at these bins, right? You take a look at how much current flows into each bin versus the mass of each bin, and you guys look at these kind of readouts in your chemistry classes, right? Is this something you do? I don't know what you use your axes, but it's basically ion current in each bin versus the mass that is expected to land in that bin. Okay? So again, this is a simplified model of a mass spec. There's a little bit more to it than that. But you can see hypothetically what the use is of a velocity selector. It's one thing that allows you to control for speed. Now, with a mass spec, that's one use of this kind of technology. This device also could be used for more nefarious purposes. It could be used to make a nuclear weapon. Okay? So, uranium. It's a naturally occurring thing. You dig it out of the ground. And what you will find when you dig it out of the ground, you will find that it's mostly uranium-238. And that's like 99% of it. And then like 1% uranium-235. So the 238 is the sum of the protons and neutrons in the nucleus. You guys do this kind of stuff? Okay, good. And the uranium-235, well, it's still uranium, so it's got to have the same number of protons. The difference is it has 3 less neutrons. 3 less neutrons. It's a different isotope of uranium. There are others, by the way, but these are the big 2. So I should say a few brief words about the role of neutrons and what they play in stability of a nucleus. Here's an interesting thing you find out about protons. We, of course, know that they're like charges, so they violently repel if they're placed close together. But they have a little secret. If you push them together, overcoming these colossal forces, they stick. Okay? So if you get them close enough, there's a even stronger but extremely short-range force called the strong nuclear force. Okay? So you can get them really close together. The violent repulsion that they experience due to the electrical force, I'm drawing that even bigger because they're even closer, is made up for by the strong nuclear force, which is able to actually attract them so strongly that it overpowers their repulsion. Now, I'm not drawing the forces because the forces are very large and pointing towards each other, and I just don't have the room to. So I'm imagining it as just like a little dot of glue. Now, literally, the exchange particles for the strong nuclear force are called gluons. Okay? So that is how any nucleus stays together that isn't a hydrogen, right? A hydrogen is a single proton, but you might wonder, how do any of the higher elements, how do the nucleus keep from flying apart when there's obviously a bunch of charged particles in there that are protons and they're plus, they're all like, so they should push apart. And they do. But strong nuclear force at very short ranges kicks in and holds it together. So there is a kind of a push-pull here between the electrical force wanting to fly it apart and the strong nuclear force putting it together. And there can often be a kind of a nice edge balance between those two. If the electric force wins out even slightly, the whole thing flies apart. Whereas if the nuclear force wins, it can keep it together. So this is where the neutrons come in as the peacemakers. Okay? Yes, there was some neutrons involved in the negotiations with the administration and the faculty. Okay? So neutral arbitrators. Now neutrons, they do not at all participate in the electrical force. So that's why they haven't gotten a single mention in this entire class except the first day. But they do participate in the strong nuclear force. Strong nuclear force is between protons and protons, neutrons and neutrons, protons and neutrons. All the constituents of the nucleus participate in this. And so you can immediately see the advantage of having this extra spacer. It allows the protons to be a little further apart. And so the forces threatening to fly the nucleus apart are lessened. So the neutrons are like the peacemakers. Okay? Neutrons always lend stability to a nucleus because their whole job is to keep the nucleus together while making sure that the protons are kind of further apart, right? They don't attract each other. So that's what we have, is that if there are 3 more peacemakers in uranium-235, it's highly stable. But if you have 3 less of them, there is a finite possibility that there may occasionally be one of these things that flies apart, and so you will have something called radioactivity here. So uranium-235 is what we call radioactive. Now the thing to know is when a nucleus flies apart, it can release a tremendous amount of energy, the famous equation E equals mc squared. So when you have nuclei breaking apart, there's a tremendous release in energy. So if you do that slowly, you can use it for very clean power. But if you do it fast, you can make a weapon out of this. The only problem is that if you wanted to get uranium-235 out, it's only 1% of naturally occurring uranium. And it's sifted in atom by atom, so that is going to be a very difficult task to get it out. Okay? That is known as the process of enrichment, right? It's getting the percentage of uranium-235 in a sample to a much higher level. So what can we use? We could use something like this. We could take the uranium, turn it into a gas. I think they chemically bond it with something to make that easier. It's like uranium hexafluoride or something crazy like that. They make it a gas. They shoot it through something where they can have the masses separate out. So this would be less mass. This would be uranium-235, and this would be your 238. The mass difference is ever so subtle, so the bins aren't that far apart, and oftentimes you'll get stuff falling in the wrong bin. That's why you have to run it over and over and over again. That's the process of enrichment. Okay? This particular device is called the Calutron. They used this in World War II. The Cal is for Berkeley. This was over across the bay that was doing this. This is the uranium that was put into the bomb that was dropped on Hiroshima. Okay? So they don't use this anymore just because separation like this tends to be very intensive. There tends to be a lot of cross-contamination of the 2 bins. The problem is that when you have positive charges flying into one bin and positive charges flying into another bin right next to it, the 2 tend to repel each other, which really tends to make it hard to sort them out. So nowadays they use centrifuges. You may remember a couple years ago, they talked about, you know, what was it, like Iraq was buying centrifuges and stuff like that. So that's how enrichment happens now. Enrichment is a very difficult process, and that's a good thing because uranium is found everywhere. Okay? You can find this all around the world. No one has a monopoly on uranium. Most countries have some, but the difficult thing is sifting out these uranium-235 atoms, increasing the percentage. So this is something that is hard to do in secret. It's hard for anybody but a national government to engage this in the kind of behavior because it's very, very large budget, hard to hide. So the concern is partially that certain governments will do this, and also that some terrorists or something like that will get their hands on some that is already enriched by somebody else. There's a lot of nuclear material that, for instance, went missing with the fall of the Soviet Union, so no one knows where that stuff is. Okay. So one of the biggest things besides trying to get other governments to not begin the process of enrichment of uranium is to try to figure out where is everything and secure it. Okay. So that right there, just a little bit about nuclear physics. That's going to be probably the beginning and end of what I'm going to have a chance to talk about in class about that. So I did want to give you a little bit of a sense of the strong nuclear force, isotopes, enrichment, all that stuff. Any questions on that? Okay, so I mentioned that this has a tie into something called the Hall effect. So let's talk about that. So here's what I have. I have a battery. I'm going to have some kind of conducting plate. And of course, what that's going to accomplish is that charged particles are going to flow as we normally pretend. Positive charges flow towards lower voltage. They're going to shoot through the middle here of the plate and then just continue on their merry way. So if we were to grab one of our voltmeters, we would certainly measure a voltage difference between here and here. Of course, I can characterize this as a conductor, but of course, real conductors do have resistance, right? So there'll be a voltage drop. The left end will be the higher end. The right end will be the lower end, right? So there will be a voltage difference between here and here, right? But if I were to similarly connect the probes of the voltmeter not across the left and right ends, but across the top and bottom of the same spot, like here and here, I would not expect a difference there, right? Because this is just the same point of the journey from higher to lower voltage. Well, let's change that. What I'm going to do is I'm going to apply a magnetic field in this entire region. So from some external means, I'm going to apply a magnetic field into the page on the plate. Well, what is that going to do? I do my right-hand rule, and I slap my B into my B, and I have it, the force is up. So these charged particles are not going to shoot down the center of the pike here. They're going to be deflected over here, going like this. So while they have the ability to move laterally, they will tend to drag across the top side of the plate. It should be noted, by the way, that whenever we have a conducting wire or any kind of thing that has a current through it, we take it as being neutral overall. So it's not just positive charges alone. There's, of course, moving against a background of hypothetical negative stationary charges. It's weird to think of it all backwards, but if we think of the positive charges moving, we have to think of the negative charges being in place, right? So here, we're going to have negative charges, basically, that are going to be basically unpaired, right? The positive charges tend to drag across the top, so we're going to find negative charge across the bottom. So if you took a look at that compared to our original system, it almost functions like a capacitor. In fact, it basically functions the same way. There will be a lateral electric field here. And as far as how many charges drag across the top, well, as many drag across the top so that no more would want to go. So essentially, there'll be some proportion of charges that are dragged across the top, and the rest don't feel like it, so they're going to shoot across the middle. Essentially, it's the exact same thing as the velocity selector, except the pluses and minuses are not separately provided. They come from the charges that are shot into the region. A certain percentage will drag across the top and make it so nobody else will. Okay? So it looks very much like a velocity selector. Just remember that these charges are dragging across the top. Okay? So now, we will measure a lateral voltage difference across the two sides, right? If we were to put a voltmeter across here and here, which side would be the higher voltage, the top or the bottom? The top, yeah, it's got the positive charge, right? Positive charges make voltage hills, negatives make voltage valleys. So now we get a lateral voltage difference between here and here, with the top plate being the higher voltage. So aside from the main voltage difference, which is of course left to right, we drop voltage going to the right, we will find that if we check the voltage difference between the two sides,